What are we doing on Thursday lab? Do we need to prepare for it?
Yeah, I'll talk about Thursday's lab today, so we can get prepared for it. All right, any other questions? No. All right. How about that calculation yesterday? Was that okay for figuring out for the milliliters of base? You kind of get it. Somewhat. We could go over some more of those. We'll just do a generic one rather than working with numbers. But if we're looking at say a diprotic acid, we're going to have two equivalence points here. Let's say the equivalence points are going to be right in the middle of this rise here. The same thing here. That's how we tell where the equivalence points are from the graph. So we graph this data out, we get a curve like this, we can find it. And this volume would be the equivalent volume, you know, what amount of base we need to neutralize that. These are supposed to be equal, but the drawing doesn't look that way. Right in the middle of this is what we call the half equivalence point, right? The half equivalence point, we have the pKa1, is the pH, and the pKa2, pH. And so what we could do is we could use the shortcut method, or do you want to do the long way or the short way doing this?
The one that works all the time.
The one that works all the time would be the long way. Do the long way. All right. What typically we do is we'll match up the pHs. You know, I mean, map out the pHs, which means we kind of have an idea of where we are. You know, this would be the excess base or excess sodium hydroxide plus weak conjugate base. This would be the second equivalence point here. This would be the first equivalence point here. This we call the buffer region 2. This we call the buffer region 3. I mean 1, sorry. And so normally when we're approached with a problem, you know, how many milliliters would it take to get to a certain pH? The first thing we have to figure out is in what region are we, you know? And that's going to be the case for both, you know, for both the long method and the shortcut method. And so what we try to do is we try to get the pHs that we can get rapidly. The pHs that we can get rapidly are like the pKa's, you know, those are quick and easy to get. And so if we're looking at a titration curve for diprotic, it'd look like this. If we have a triprotic, maybe we should do that. Let's do that. Yeah, we'd put another lump on there if we can see that particular pH. And so let's take a look at a triprotic acid, like a citric acid. Citric acid it did the other day. Citric acid behaves, should behave okay. Citric acid has the formula H3 C6H5O7. C6H5O7. Carboxylic acid. What we're going to do is, this is kind of a long formula, so we're just going to abbreviate H3CIT, where CIT is the citrate ion, C6H5O7 3-. And so if we're looking at something like citric acid, then we could get the pKa's from the table here. pKa1 for citric acid is 3.12, 477. would be the second one, and 640 would be the last one. And so 3.12. Was it 6? I think I got those mixed up. 640, sorry. It's not 70, 640. All right, so this, these points are easy to place on the titration curve. So just take a look at what we expect the titration curve to look like here. It's a triprotic acid, so we expect 3 humps in the titration curve. One, let's see. The humps need to be evenly spaced, That is the equivalent volume, because of stoichiometry, is always going to be the same. So if this is 10 milliliters to hit the first equivalence point, then we'd add another 10 to get to the second, we add another 10 to get to the third. And so that keeps the numbers quite easy. 10, this would be a 20, this would be a 30. And so each equivalent volume would be 10 milliliters. Sometimes the numbers aren't so clean, like in that last example, the equivalent volume was a fraction. So it was more difficult to see. But we can figure out, at the first half equivalence point, the pH is going to be 3.12. At the second half equivalence point, which is going to be the midway point here, the pH is going to be 477. And at the third, it's going to be here, which is going to be 640. This one, we should see 3 distinct rises here, because if you look here, we're just starting at 640. We aren't starting at a very high pH. For example, in phosphoric acid, which is another triprotic acid, in phosphoric acid, pKa3 is 12.44. And 12.44 is way up here. And that's quite a high pH. That means the third equivalence point has got to be above 1244, like 13, 14. Let's say, if it's 13 or 14, well, we're using 0.1 molar sodium hydroxide. 0.1 molar sodium hydroxide in a titration has a pH of, what's a pH of 0.1 molar? That would be a pOH of 1, which means it has a pH of 13. And so pure sodium hydroxide has a pH of 13, and yet this pKa3 is at 1244, which means we aren't going to get a high enough pH. We have to use more concentrated sodium hydroxide to see it. And so in some triprotic acids, like phosphoric acid, you don't even see this third equivalence point because the pH is too high, right? In some acids, you don't even see the first one because it's too low, and because of dilution, we start out at a pH that's higher. When you add base, the pH can never go down. The pH is either going to stay kind of flat or go up, right? And so in practical terms, we might not see what we expect in theory, to see. But there's going to be a big jump here at the third equivalence point, because we got to go from 640, which is acidic, to basic, 10, 11, maybe 12. 12 getting a little high because of the solution dilution, but at infinite addition, it's got to approach pure sodium hydroxide, which would be 13. If we're using 0.100 molar. All right, and so this is a plot of the pH versus the milliliters. What other points are very easy to get? Well, these 3 are very easy, right? There's no calculation involved. You should know why, at the half equivalence points, the pH is equal to pKa. And why? The why is because we have a 50-50 mix, right? Acid, unreacted acid, and its product, the weak base. So it's a 50-50 mix of acid to base or base to acid. Then the log of that is going to be 0, right? And so the pH is just equal to pKa. What other points are easy to get? the next easiest points to get are the first equivalence point and the second equivalence point. The reason those are easy to get is because at the first equivalence point, when we've neutralized that first proton on citric acid, we're going to have sodium dihydrogen citrate and water. And so we add an equivalent amount of sodium hydroxide. This has been neutralized, so we're just left with salt and water. But this is a special salt. What's special about this salt? Is it an acidic salt, a basic salt, or an amphoteric salt? It's an amphoteric salt. You know, dihydrogen citrate's an amphoteric salt, which means that it's very difficult because we have to solve it simultaneously. We have to do both Ka and Kb, right? But somebody else has done the work for us and come up with a very simple equation that we can just use. An engineering style equation, which is what? That the pH is equal to the right, and so at the in this buffer region we have unreacted acid, which is H3 citrate, and some product, which is the conjugate base, which is H2CIT minus dihydrogen citrate. And so this is a buffer mixture, unreacted acid and conjugate base. It's a Henderson-Hasselbalch buffer. But once we've reacted all the acid, then we're just left with the conjugate base. In this case, it's amphoteric, you know. And so the pH of an H2 citrate solution is not difficult, right? If we're just left with sodium dihydrogen citrate, then the pH is equal to the pKa, right, of dihydrogen citrate, plus the pKa of its conjugate acid, which is H3 citrate or citric acid, divided by 2. And so pKa of dihydrogen citrate is 477. The pKa of its conjugate acid is 3.12 divided by 2, which gives us what? Yeah, something. It's going to be 799.
Yeah, 3.945.
3.945?
Yeah.
So about 395. So we'll just put the 395 in. All right, and then at the second equivalence point here, we're going to run into a similar scenario, because at the second equivalence point, we're going to neutralize the next hydrogen. So we're going to take our sodium dihydrogen citrate, neutralize that second proton on there to form sodium monohydrogen citrate and water. Okay, so on the way to neutralizing that, we're going to neutralize some of this acid and create its conjugate base. So we got weak acid, weak base, and they're conjugates of each other. And so the next buffer system is going to be the dihydrogen citrate, monohydrogen citrate buffer. And so for the first buffer system, the pH is equal to pKa of citric acid plus the log of dihydrogen citrate over citric acid. In the second buffer system, the pKa is different. It's going to be dihydrogen citrate in this case, so the pH is equal to pKa of dihydrogen citrate plus the log of monohydrogen citrate over citrate over dihydrogen citrate. But once we've neutralized all that dihydrogen citrate, then we're just left with monohydrogen citrate. Well, monohydrogen citrate, that's also amphoteric, right? Monohydrogen citrate, we can figure out the pH. What is the pH of a solution of sodium monohydrogen citrate? Well, the pH is very difficult to get because we solve it simultaneously, but we're going to skip all the hard work and just go to the equation, which is the pKa of monohydrogen citrate plus the pKa of its conjugate acid, which would be dihydrogen citrate, divided by 2. And so this is going to be monohydrogen 640 plus 477 divided by 2, which gives us what is it? 5.585. 5.585. Or 5.59. And so this is 5.59. And so now we know that buffer region 2 is bounded by 395, between 395 and 559. The pH is there, would be buffer region 2. And so if I ask, you know, what is the number of milliliters required to reach a pH of 5.00, then you know, well, that's got to be in buffer region 2. And that's going to dictate how we set up the problem. Versus if I asked you, you know, how many milliliters would it take to get to a pH of 2.95, then that's got to be in buffer region 1. Right? So we can get some kind of ideas. We know that this has got to be, I don't know where this has got to be here, but this would be at the third equivalence point. At the third equivalence point, what are we left up with? Well, we've neutralized all the protons, and we're going to be left with a citrate solution, sodium citrate. And so at the third equivalence point, we'll neutralize the last remaining proton. And so we'll take our sodium monohydrogen citrate with sodium hydroxide. This is going to give us sodium citrate and water. Well, sodium citrate is that amphoteric? No. This is a tribasic base. And so we got Kb1, Kb2, Kb3, and Kw. If we want to figure out the pH, it's just the base solution. Usually pH requires what? Kb1, Kb1 and Kb2, all the Kbs plus Kw. We just want to figure out the pH. Usually just 1, right? Kb. Usually, except let's take a look at the Kb values here. 7.5 times 10 to the minus 4. So Kb1 is 7.5 times 10 to the minus 4. Kb2 is 1.7 times 10 to the minus 5. Kb3, oops, no, sorry, I made a mistake. I'm not getting the Kbs, these are the Kas. I need to calculate the Kbs, so let me go ahead and calculate the Kbs and see what the Kbs are. And so Kb1, I guess I can brace this here. All right, Kb1 is just of citrate. It would just be the Kb of citrate ion. You see, Q3 minus, which is going to equal Kw over the Ka for what acid? No, not for citric acid. Monohydrogen citrate. It's conjugate acid. So this is 1.0 times 10 to the minus 14 divided by monohydrogen citrate. It's Ka. 4.0 times 10 to the negative 7. Which gives us a Kb of 1/4, 2.5 times 10 to the negative 6. Is that right? Or 7? I don't know. 7? 8? 10 to the negative 8.
Now we should worry about Kw.
Well, let's see. Oh, that's Kb1. Let's Kb2. Kb2 is going to be the Kb for monohydrogen citrate, which is going to equal Kw over the Ka for dihydrogen citrate. Ka for dihydrogen citrate is 1.7 times 10 to the minus 5. which gives us what?
5.88 times 10 to the negative
5.88 times 10 to the negative 10. Yeah.
We should worry about KW already.
Do we really want to worry about KW? KW is 10 to the minus
7.
no 14.
Still out of our spectrum.
So 10 to the minus 14, is that going to yield much hydroxide? In the base solution, we're looking for the biggest hydroxide contributors. The biggest one will be citrate, followed by monohydrogen citrate. Monohydrogen citrate is 10 to the minus 10. Do you expect much additional hydroxide from this? And so we're probably okay with just KB1.
I think your charge values are wrong on those. Isn't HCIC 2 minus and
Yeah.
H2 1 minus?
Yeah, you're right.
Wait, excuse me, I thought, KW would contribute a hydroxide of 10 to the minus 7.
If there's no common ion. But if there's common ion, it's going to be much smaller than 10 to the minus 7. The same thing here. I mean, KW is 10 to the minus 14, and that yields a hydroxide ion concentration 10 to the minus 7 in pure water. But you know, this is a much bigger K value. You know, KW is both Ka and Kb. And so when we compare it, the Kb of water is 10 to the minus 14. The Kb of monohydrogen citrate is 10 to the minus 10. Which one's going to yield more hydroxide? This. Kw is both equal to Ka and it's equal to Kb.
So the KB of water is not 10 to the negative 7, but it's...
No, the Kb of water is 10 to the minus 14. The Ka of water is 10 to the minus 14. Water is very unusual because water is both Ka and Kb. Water hydrolyzes water to form hydronium. Well, that's Ka, right? Water also hydrolyzes water to form hydroxide. Well, that's Kb. This is both Ka and Kb. And so Kw is equal to Ka, which is equal to Kb for water. But anyway, getting back to this, it looks like we're okay with just KB1. We'd worry about KB2 if it were
10 to the negative 14?
no, 10 to the negative 14, we'd worry even less about it.
Oh, within reason of K.
We'd worry about KB2 if 9 or 10, we wouldn't worry. 10 minus 9, 10 minus 10, I wouldn't worry about it at all.
10 to the negative 12.
No.
Wrong way.
Not to, no, yeah, we're going the wrong way. We'd worry about KB2 if it were significant, right?
Right.
And what is significant?
Something's within, I thought it was 2, like 2 values, like 100.
Like, yeah, like 10 to the minus 2, but this is nowhere, you know, it's not that big. It's very small, in fact, right? And, this is just a check. You know, the rule of thumb usually works until it fails, right? And so when does it fail? You can just use the first step in a multi-step unless the second step is big, is significant, right? And so this one is probably just the first step is going to be okay. And so, and if you're uncertain about it, you could just do the calculation. It doesn't take that much time to do 2 steps in this particular calculation.
We're not sure that we're gonna worry about KW. Should we do that too?
I wouldn't worry about KW at all. I would think worrying about KW is going to be a waste of your time because it's not going to make any difference in pH. So let's figure out the pH of this, except, you know, to get the pH of this, we have to be careful because in the shortcut regions like here, here, and here, you know, the pH of a buffer does not depend on the concentration. It just depends on the ratio, base to acid. For amphoteric, as long as we have significant concentrations of the species, this doesn't depend on the concentration. It's just pKa divided by 2, right? But here, you know, citrate is going to depend on its concentration. The more dilute it is, a pH will differ versus more concentrated. And so let's take a look. And so basically from here on, we can't use the shortcut. From here on, we have to use the long method, because from there on, the concentration is going to have an impact on that.
Why doesn't it have an impact earlier?
Because the pH in these regions is dictated by these two equations. pH is equal to the pKa plus the log. And so if you were to dilute it, you would dilute, let's say I cut the concentration in half. Well, you're cutting the concentration in half for both of these, so that factor of 1/2 in the numerator cancels out the one in the denominator, so it doesn't depend. The same thing. And then the amphoteric species, it's just pKa1 times pKa2, just generic. I also call it pKa plus pKa divided by 2. And so that doesn't depend on the concentration either. And so from this point on, it depends on the concentration. And at the initial pH here, this depends on concentration, because it depends on how concentrated you make that acid. This is why we try to make it as concentrated as possible to get the pH down low, so that we get a bigger hump here, the first equivalence point. And so setting up a problem like this, let's say, I'll keep the number simple. We just have 10.00 milliliters of 0.100 molar citric acid. We're going to titrate this with 0.100 molar sodium hydroxide. And so to get to the third equivalence point, we'd have to know this. We'd have to know that we're going to add how many milliliters of sodium hydroxide to get to the third equivalence point. Well, one equivalent would be 10 milliliters because of the same concentration. So 2 equivalents, 20 milliliters, 3 equivalents would be 30 milliliters. So we're going to add 30.00 milliliters here. And so altogether, we're going to end up with 40 milliliters of solution. And then we do our solution dilution. Sodium hydroxide is going to be a 30 to 40 dilution of 0.100 molar. Is that right?
30 to 40?
Yeah.
Was it 10 or 40?
No, the acid is. And so this is going to be 0.07500 molar, keeping the right number of sig figs. And then the citric acid is going to be a 10 to 40 dilution, 0.100 molar. This is going to give a 0.02500 molar. There are little shortcuts you can do, but the thing is, you have to get the standard. You do the standard calculation first, you master that, and then you work on all the shortcuts. And so, let's just do it the same way. Like I said, you could do any problem in here the same way. And so you just take the strongest acid, citric acid, and the strongest base, sodium hydroxide, react those. This is going to form sodium dihydrogen citrate plus water. We always do it one step at a time, one proton at a time. And so the citric acid is 0.02500. Sodium hydroxide is 0.07500. What's K for this reaction? What's K for this reaction?
3.1 Ka.
The Ka? Ka for H3CIT. Ka, A stands for what? Acid. In the book calls it acid ionization. I call it acid. Because not neutral, I call it acid. Ka, I call acid. maybe it didn't register. I called a bunch of times the same name, acid
Hydrolysis.
hydrolysis. Yeah, acid hydrolysis. Is acid and
Water.
water. Acid hydrolysis. KB is base hydrolysis. I don't call it base ionization because ionization is, I think, the wrong word for it. It should be base hydrolysis because it's base plus water yields hydroxide, conjugate acid. Is this acid hydrolysis? No, this is not acid. That would be acid plus water is Ka. Acid plus water is, Ka is very large, right? Was water a good base? No. No, there's better bases, like ammonia. Or even better bases like sodium hydroxide. And so what would the K for this reaction be? This is a better base than water. Much, much better base than water.
Very, very low.
Very, very large, yeah. Because Ka, or acid plus, well, wait a minute. This is a weak acid though.
It's a weak acid, strong base.
Yeah. And so KB is, well, KB for a strong base is very large. And so KB for a strong base would be the base plus water. But this acid is much stronger than water. And so this should be very, very large. Right? Does that make sense? And so we know that this is going to go to completion. So this is going to go to 0. This is going to be 0.05,000. This is going to be 0.02500. All right, so what do we have left over? We have strong base and weak acid. Or actually, this is amphoteric. Strong base, and this was conjugate base, but you know, this being the conjugate base, since it's amphoteric, can now act as the acid because this is going to be the strongest acid around. And so we have the strong base plus the strongest acid would be sodium dihydrogen citrate. So we'll just take sodium dihydrogen citrate plus sodium hydroxide. It's going to yield sodium monohydrogen citrate and water. This is 0.02500. This is 0.05000. This is 0. This should be very, very large. So limiting reagent, sodium dihydrogen phosphate. We're going to have some leftover excess sodium hydroxide and generate sodium monohydrogen citrate. And so we have strong base and amphoteric. This amphoteric will act as the acid. And so we can neutralize that last proton. So we'll take our sodium monohydrogen citrate plus the remaining sodium hydroxide to make sodium citrate and water. So this is 0.02500. This is 0.02500. This is 0. And so this is equal molar. In other words, we have an equivalent of sodium hydroxide. We're going to use to neutralize that. Or in other words, it's stoichiometric. There's no excess, no limiting. And we're just going to be left with product, 0.02500 molar. And so this is the concentration. The concentration is going to impact the pH. So what we're left over with is just a tribasic base. And so the next step would be, well, the base and will react with the strongest acid present, but now the strongest acid present is just water. We don't have any more citric acid or any of its derivatives. And so the citrate will react with water to produce what? Yep, monohydrogen citrate and hydroxide. Technically, this is like going backwards, but not exactly. Because the hydroxide has been generated. This is KB1, which we calculated. And so the initial is 0.02500. Water's out. This is 0, this is 0. So at equilibrium we have 0.02500 minus x, and x. So KB1 is going to equal x squared over 0.02500 minus x. We use the simplifying assumption here. We'll just get x squared over 0.02500, which means that x is equal to what? What was KB1 again? 2.5 times 10 to the negative 8. Thanks.
2.5 times 10 to the negative 4.
What did you get?
2.5 times 10 to the negative 5.
Times 10 to the negative 10?
Yeah.
Times 10 to the negative 5?
Yeah.
Okay, let's calculate a percent change. A percent change would be 2.5 times 10 to the negative 5th divided by 0.025, or 2.5 times 10 to the negative 2. And so this gives us times 10 squared.
100% is 0.1.
It's 0.1%?
Yeah.
All right, then we're good. We double check this to make sure. Calculate that.
Go to the pKa.
Yeah, make sure it's equal to KB in this case. All right, would you think KB2 would contribute much hydroxide? There are two reasons why I don't think KB2 would contribute much hydroxide. One, KB2 is 10 to the minus 10, which is pretty small. And two, there's going to be common ion, 10 to the minus 5 molar hydroxide already, and so we don't expect KB2 to contribute much. So we just calculate the pH based on this. So ignore KB2, KB3, and KW. They'll save us a lot of time. These calculations are time consuming. Let's see. And so what is the pH here? Well, I'll probably calculate the pOH first.
Yeah, that's all good. So pH should be 9.39.
pH is 9.39? All right. 9.39.
9.397.
9.397, so 9.397, which would give us about 9.40. 9.4.
So is that the third equivalent?
That's a third equivalence point, it's quite high. And so we're looking at pHs past 9.39 would be the excess, or 9.40 would be the excess
Okay.
sodium hydroxide region. Called it. Okay, then we need the initial pH here, and then we have the curve fairly well mapped out. The initial pH is just 0.100 molar citric acid. Ka1 for citric acid is 10 to the minus 4. Ka2 is 10 to the minus 5. They're kind of close, huh? So if we look at Ka1, 7.5 times 10 to the minus 4. Ka2,
1.7 times 10 to the minus 5.
1.7 times 10 to the minus 5.
Yes.
Ka3,
4.0 times 10 to the negative 7.
4.0 times 10 to the negative 7. Kw is 1.0 times 10 to the minus 14. Make sure you memorize this one for sure. And it should be ingrained. Well, here, should we just do Ka1 and ignore the others?
No.
You got it.
I'm starting to worry about Ka2 2 because Ka2 is about the same order of magnitude as Ka1. And so in this case, I might do Ka1 and Ka2 to figure out, but probably wouldn't worry about Ka3 and Kw because it becomes less and less significant as we go, right? All right, so let's go ahead and do the step 1. So if we're just at the beginning of the titration, we just have citric acid, and so this is the strongest acid. The strongest base around will be water, and so this is a Kb equation. Base plus water gives us, oh no, this is not Kb, this is a Ka equation. Acid plus water. This is the strongest acid, this is the strongest base.
H3O plus H.
H3O plus plus, yeah. H2Ci2 minus.
Yes.
Okay, we start off with 0.100 molar, nothing for water there, 0, 0. Change. So at equilibrium we have 0.100 minus x. This is going to be x. This is going to be x. So Ka is 7.5 times 10 to the minus 4, which is equal to x squared over 0.100 minus x. I'll just use the simplifying assumption. This is going to be x squared over 0.100, which is going to give us an x value of what?
I got 8.66 times 10 to the negative 1, 2, 3.
Times 10 to the negative 3. Ah,
Not a digit.
no. That's enough because, what's the percent change? Can you see the percent change? 8.66%. Too high, it fails. Yeah. So that means we have to use the quadratic.
Where's that quadratic calculator?
So let's get this into quadratic form. So it's going to be x squared plus 7.5 times 10 to the minus 4x minus 7.5 times 10 to the minus 5 is equal to 0. So what do you get for?
Quadratic equation, so
Yeah. 8.29 times 10 to the negative 3. Okay. So you can see this was kind of quite off here, 8.66. 8.29 times 10 to the minus 3. All right, let's plug those in to get the concentrations back here. And so the hydronium is, I'm just going to write this in decimal form, 0.00829. 0.00829 molar. This is going to be 0.100 minus 0.00829. 1, 7. .09171 molar. So you should double check this to make sure that those multiply out to K, right? Yes, good, thanks. All right, so now the question comes up, should we go on to step 2 or should we just stop here?
step 2.
All right, well, there's a little bit of uncertainty because step 2 has kind of a big order of magnitude. I mean, not big, but it's comparable, right? And so maybe we should go on to step 2. Step 2 would be dihydrogen citrate. Dihydrogen citrate can also contribute some more hydronium to the solution. So if we take dihydrogen citrate plus water, this will yield some more hydronium plus monohydrogen citrate. Well, the reason we're considering it is because the Ka for this step is comparable, 1.7 times 10 minus 5. And so let's plug in the numbers here. We got 0.00829 molar dihydrogen citrate and 0.00829 molar hydronium and 0 molar monohydrogen citrate. And so on the one hand, yes, it should contribute significant. On the other hand, it might not because of the common ion. We've got a lot of common ion here. It's going to key. Yeah. And so at equilibrium, we're going to get 00829 minus X for the citrate. For the hydronium, 00829 plus X, and then X. Ka2 is 1.7 times 10 minus 5, which is going to be 00829 plus X times X over 00829 minus X. We're going to use the simplifying assumption here, so that's just equal to X. If that's equal to X, then let's calculate the percent. The percent change would be 1.7 times 10 to the minus 5 divided by 0.00829 is 100. 0.2%. 0.2%? Okay. So the common ion effect was significant there. We didn't get much change here, so the simplifying assumption worked there. Okay, let's calculate the concentrations. Did step 2 add a significant amount of hydronium? And so looking at this, we got 0.00829 plus our X. Yeah, so I need 4 zeros and a 1, 7, 5, is that right? No, 1, 7. 4 zeros and 1, 7. So this is going to be 0.08307 molar. So yeah. Okay, over here we lost a little bit, right? Minus 0.00017. So it's 3, 8, 7. So we go from 829 to 827.
Does it perturb?
That's a question. It changed it, right?
Yeah.
So would that change? Now the concentrations are different. So if the concentrations are different, our double check is not going to double check, is it? Well, 2 ways to tell if it perturbs. One is to use these new concentrations and recalculate our K in step 1. Or 2 is just to make a rough judgment. You know, when we look at this concentration here, it's 0.00829, which we would round this to 0.0083, and this would be rounded to 0.0083, and this one would be properly rounded to 0.0083, and before it would have been rounded to 0.083, so it doesn't seem like it perturbed. We'd say, you know, since they round to the same numbers, then it doesn't really change it. And so we didn't really have to do step 2, so it must have been, you know, the common ion effect. It really didn't add that much additional hydronium.
How do we know if the common ion effect is happening or is it not?
How you know is you see it. If you have some ion there to begin with, before the reaction takes place, the product inhibits the forward reaction. This is Le Chatelier's type principle. And so you would see it. The common ion should be readily apparent. And so if we calculate the pH based on step 1, what does it come out to?
Step 1?
Yeah. before. You calculate the pH before we added step 2, which is 0.0829. The negative log of that would be what?
First one is negative 2.08, or sorry, positive 2.081.
2.081, okay.
And then the second one is 4.76. It changed a lot.
No, the second one would be this, the negative log of this. 2.08. So, really close. If there was a more significant increase and decrease here, then we would have to solve it simultaneously. Unfortunately, we didn't. And so this is 2.08. All right, so now we have it really well mapped out, would you say? And so there are certain points that we can get quite quickly here. Actually, we'll take a break right now, and then we'll look at some of the points we can get quite quickly.
I was so stuck in your bottom and cracked. You have a new grass, Sandra.
I didn't have my data recorded last time.
Okay.